In 2017, the wife of an Australian senator was hit by a speeding mobility scooter, causing an intense political debate about severely restricting and regulating their use. But these scooters also go a long way in helping a lot of people with mobility difficulties feel more independent and empowered. In fact, these scooters are part of a larger class of compact vehicles known as personal mobility devices or PMDs, which have been rising in popularity in recent times. Although they typically travel at very low speeds and come in small form factors, they are mandated to traverse in spaces traditionally reserved for pedestrians, which make them quite dangerous. Our research is motivated by the fact that these devices could greatly benefit from the recent interest in autonomous vehicle technology, both in terms of their general safety and overall functionality. One of the fundamental challenges in introducing autonomy to these devices is solving the localization problem, since an accurate position estimate is instrumental in safe and robust navigation. GPS in dense urban environments is unreliable for this because of multipath errors and ionospheric interference. So most fast-moving self-driving vehicles use a suite of sensors ranging from LiDARs to cameras, coupled with dense 3D point cloud maps of the environment. But this approach takes a lot of resources and requires expensive sensors, which makes them unsuitable for resource-constrained applications such as PMDs. In fact, the limited operating conditions of these PMDs, such as lower speeds, more defined paths, means we should be able to carry out localization with far less resources. Thus, our proposed system uses a vision-only localization approach, coupled with a very sparse 2D map. Traditional state-of-the-art vision-only navigation can broadly be looked at in two categories. Feature-based techniques that use low-level handcrafted features for motion estimation, such as OBSLAM, RTAB map, and appearance-based techniques that use direct pixel intensities for motion estimation, such as LSD-SLAM and DSO. However, making a pre-built map using these techniques that can be reused over long time frames becomes difficult due to appearance changes and dynamic objects found in typical urban outdoor environments. So these approaches generally rely on SLAM or plain visual odometry, which is computationally expensive at scale and prone to drift, needing robust loop closures to fix, which isn't always guaranteed. In contrast, the proposed work enables us to carry out localization on a sparse, pre-built map using persistent high-level semantic features found in typical urban environments. It does so by using a deep learning-based perceptual front-end that extracts these high-level semantic features, which are then fused with odometry data under standard extended Kalman filter framework. Let us now look into each of these components in more detail. Let us first look at the perceptual front-end, which consists of two categories of feature observations. Number one, ground surface boundary observations, such as curbs, pavement edges, manhole covers, etc. Second, environmental landmarks such as street lamps, trees, parking meters, and so forth. The ground surface boundary observations are obtained using a ground-facing RGBD camera. Ground surface edges are extracted using a CNN-based edge detection known as holistically nested edge detection, or HED. These ground surface edges are then projected to the ground plane using the depth information from the RGBD camera. The corresponding map for these ground surface boundaries is represented using a vector distance transform. This VDT representation means no enforcement or extraction of geometric primitives such as lines or curves on the ground surface is required, as it implicitly captures the geometry of the environment. Furthermore, no data association is needed either. The environmental landmarks are extracted using the YOLO version 2 object detection framework, trained using transfer learning. A monocular camera is used to obtain the bearing-only observations to these detected landmarks. This, combined with the semantic information given by the CNN, form the second category of observations. The corresponding map for these observations is simply the 2D location of these features and their corresponding semantic labels, which aid in data association. The observation data is then used in the EKF backend of the framework to estimate the pose of the PMD. Following the standard EKF formulation, we propagate the state and the associated covariance matrix in time using the velocity motion model in the prediction step. When a ground surface boundary observation is available as ZT, the disparity between the expected and actual observations, or the innovation, can be obtained by transforming the observations into the map frame based on the predicted pose and querying the VDT. In the case of a landmark observation, the set of bearings theta t and the corresponding semantic labels LT are used to calculate the innovation based on the set of expected observations at the predicted pose. In both cases, innovation covariance is used to statistically eliminate outliers. A more detailed explanation of this entire process can be found in the paper. As in the standard EKF, the Kalman gain is then calculated and used to update the state and its associated covariance. This framework was implemented on a modified off-the-shelf mobility scooter. A rear-mounted tilted rear-sense D435 sensor is used to obtain the ground surface observations. Two more rear sensors are mounted at 45 degrees to the heading of the scooter to provide landmark observations from the sides of the road. An RTK GPS and Hokkyo laser is also mounted purely for evaluation purposes and map building. The primary computing unit of this platform is an NVIDIA Jetson Xavier. Two experiments were carried out using this hardware platform. The first was to validate and tune the algorithm. For this purpose, continuous ground truth was required. Now, RTK GPS provides centimeter level accuracy, but under the condition that a clear skyline is available free of any multipath errors. So, for this purpose, Wentworth Park in Sydney was chosen. As indicated in the diagram, the error of the framework relative to the RTK readings were within the reported 2 sigma covariance bounds, validating that the EKF is well tuned. In order to demonstrate the capabilities of the proposed framework in a less controlled and more real-world urban setting, a second set of experiments were carried out in an 8,000 square meter area in Sydney, Australia. However, unlike the previous experiment, fixed RTK GPS measurements could not be obtained continuously due to buildings and trees obstructing the skyline. Therefore, this experiment provides a more qualitative demonstration of the framework's capabilities when overlaid on a satellite map of the environment. The results are also compared with GPS, shown here in orange, and the localization mode of RTAB map, which is a popular open source laser and RGBD SLAM package, shown in red. The RTAB framework was indispensable in the map building process. However, mapping involved running RTAB on data collected in tightly controlled small loops within short time frames, typically under 1 hour, during times of the day when the environment remained relatively static. However, on a general run performed at a more dynamic time of the day with no opportunity for loop closure results in eventual drift as seen in the diagram. A potential failure scenario of our system can be observed from section B to C, where ground surface observations are unavailable and landmarks are sparse. In this particular scenario, the reported uncertainty increases as expected, which is powerful information for a high-level motion planner to take into account. When more information is fused, this covariance eventually drops. To tackle the problem of sparsity of features, we are currently looking at the following solutions. Number 1, using a 360-degree omnidirectional camera. 2, fusing cellular assisted GPS. And 3, increasing the overall database of features. We are also looking into more comprehensive map building and maintenance strategies, which also includes incorporating uncertain information into the sparse maps currently being used. In summary, utilizing CNN-based ground surface and environmental landmark observations enables our framework to carry out vision-only localization on a pre-built map that is suitable for resource-constrained applications such as PMDs. Thank you.